Welcome back, everyone. So today's exciting lecture deals with the topic of friction. We've already talked about friction a little bit as the force that slows things down that are moving, but we're going to look at a different way of calculating friction and basically making things a little more complicated, as we tend to do. Alright, so friction depends on two things: the types of surfaces rubbing together. In the equation, that is symbolized by the Greek letter mu, mu. So here we have the mu. And the other thing that influences it, a lot of people think it's the weight of the object, but more specifically it's how hard the surfaces are being pressed together, and that is measured by the normal force. Often this equals the weight of the object, but it doesn't have to, and it won't always. Okay, so here we have our new equation, sometimes called the fun equation if you look at the F mu n. So we have friction equals the coefficient of friction times the normal force. Okay. Now these coefficients of friction are usually between like 0.2 and about 1, and you'll notice that they're unitless because friction is measured in newtons and the normal force is measured in newtons, so it's a unitless quantity. This is not given the same status as Newton's second law, F equals ma. This is considered more of an approximation, and you'll notice when you think about this a little more, if that's all it depends on is the normal force and the surfaces involved, you get some interesting situations. If you think about a textbook laying flat on its cover, it's going to have, and if you're trying to slide that across a desk, it's going to have a given coefficient of friction given by the materials, the desk and the book, and it's going to have a normal force which is going to equal the book, and so you'll get a certain friction force. Now if you take that same book and you pick it up on its spine, well, you still have book material and desk material, so you didn't change mu, and the weight of the book didn't change either. So this equation actually tells us that you would have the same friction sliding a book on its spine versus sliding it on its cover, which I don't know if that's entirely true, but it's actually pretty close to a valid approximation. The idea there is when it's on its spine, there is less surface area in contact, but each unit of area is has a greater pressure on it. So that's how that works. Alright, now we distinguish between two types of friction, what we call static friction, not having anything to do with electricity. Static means unchanging, and kinetic means changing. So this is friction for, kinetic is friction for moving objects, and static is not moving objects. A little more technically than that, it's whether the two surfaces involved are sliding relative to each other. So one example is if you have a bike tire, that tire can be moving through space, moving forward, but the surface of the tire and the road are not sliding relative to each other. So with wheels, that's actually considered static friction. Kinetic friction is if the wheel starts to skid, or if you're pushing a book across a desk, like I mentioned before, where the two surfaces are sliding relative to each other. Alright, let's look at some more details about how this friction shakes out. We have the same equation here for both types of friction, but we have a different coefficient. We're going to have now I have subscripts S and K for static and kinetic. And for two given materials, you will have different coefficients for both static and kinetic. But they represent slightly different things, and let me explain what I mean by that. If I imagine that I am pushing on a table, and so here I'm going to graph my push force, and here I'm going to graph my friction force. Alright? Firstly, I'm not pushing on the table at all, so zero push force. There is no friction as long as it's on a level surface, so we can have a point here at 0, 0. Then let's say that I push with 5 newtons of friction, or sorry, 5 newtons of push force. Well, and the table doesn't move. Friction is going to respond by jumping up to 5 newtons of friction. If I push with 10 and the table still doesn't move, then friction will jump up and be 10. So you're going to have a linear response here where friction matches the push force when we're still in the static friction realm. Now if I push up to 15 and at some point in there it started moving, this is going to drop down and then it goes constant like this. So what happens here is we get a maximum amount of static friction. I don't know what it, let's say it was like 13. Once you pushed over 13, your push force kept growing, but friction couldn't keep growing. So now the object starts to move. As soon as it starts to move, you change the type of friction you're using. You're now using kinetic friction. So this part over here is static friction. Once it starts moving, when you've overcome the static friction, and you can feel that sometimes if you're moving furniture, you have to kind of give it a shove to get it sliding. Then once it's sliding, it's easier to keep going. So this part over here, and on forever, is kinetic friction. Interesting thing about kinetic friction is it doesn't change with speed, or very little anyway. So this object can go faster and faster, and the kinetic friction slowing it down remains constant. So static friction changes. It can respond to the applied forces. Kinetic friction is just constant. So if we look back at these equations, what do these coefficients tell us? Well, we have one value for the coefficient of kinetic friction, and that makes sense because we only have one value for kinetic friction. But I only have one single value for my coefficient of static friction as well. But I have all of these different values that are possible. So what this represents is the maximum amount of static friction that you can have. So in a problem, if it tells you the coefficient of static friction is, I don't know, 0.8, you don't know exactly what the static friction is unless you look at the other applied forces. So you have to be careful with that, and that's why we can just have one equation even though it changes here. Okay, so for static friction over here, it responds to applied forces, and it maxes out at some point depending on the surface. Maxes out at μs. So that's the maximum amount. Over here, it's always constant. You always have the same value. And this graph here, you'll note the maximum amount of static friction is higher than the kinetic friction, and that is going to be true in pretty much every case. So your coefficient of static friction is always going to be larger than your coefficient of kinetic friction. This is also the reason why anti-lock brakes work. What anti-lock brakes do is they try to keep you from sliding when you're braking, so they'll actually pulse your brakes on and off. But they do it so rapidly, you're essentially pulsing in this area here, but you keep a higher friction than if you started sliding and went to kinetic. So that's why that works. Okay, let's look at one example of the types of problems you'll solve. Let's say that we've got our same 20 kilogram box on our same ramp, but now I don't tell you about the amount of friction there is. In fact, I want you to find the coefficient of friction, and I'm going to give you some kinematic information. Let's say that it takes 2.4 seconds for the box to travel, let's go with 1.5 meters down the ramp. Okay, so I mean it's traveling in this direction 1.5 meters. Okay, if that's how long it takes for it to travel that far down the ramp, we can use that information to solve for the coefficient of friction. Well, this little part here is just to help us find the acceleration. And if I consider this to be the x direction down my ramp, then it doesn't matter that it's not vertical or horizontal. I can, again, kind of take that rotated picture, right? So I can say delta x is v naught t plus 1/2 at squared. Let's also assume that this started at rest. We'll assume v naught is equal to 0. It doesn't have to be, but This way we don't have a quadratic and make things even longer. Alright, so I've got my delta x there is 1.5. This goes to 0. I have 1/2 times my acceleration. This is not gravitational acceleration, right? We're not in free fall here. We don't know what our acceleration is. That's what we're going to find here so that we can use that with our force analysis in order to find this coefficient of friction. Alright, we've got the time, so 2.4 seconds squared. Just square the time, not the rest of this stuff. Okay, I rearrange. I'll kind of skip a little bit of the algebra. It works out that your acceleration is 0.52. I'm going to use this value again, so I'm going to write down several digits. If I were using my graphing calculator, I would just keep all the digits that the calculator could keep. Alright, so if this is my acceleration, I want to find that coefficient of friction. Well, I don't know exactly, just off the top of my head, how does acceleration work into coefficient of friction. So where you always want to start is with your free body diagram. So we still have same forces acting as before. We just don't know the value for friction this time. Okay, and if I rotate that guy, I end up with a picture like this. I always want to rotate it. There's my 30-degree angle. Okay, gravity here, normal force here, friction here. In the x direction, I've got, just like before, I've got the x component of gravity minus friction equals ma. In the y direction, I have normal force equals the y component of gravity. This time we're actually going to need this. Okay, so let's see where we can go from here. Well, we've got mg sine theta for this guy. Friction, I don't know what it is. But I do know that friction can always be found by doing mu times the normal force. Well, I don't know the normal force either, but I can find it by doing FGY. So this is mu times FGY. And FGY is going to be mg cosine theta, because it is this side of my triangle here, right? So if I plug that in, minus mg cosine theta, you can set that equal to, oh, I forgot my mu. It's important since that's what we're solving for. Equals ma. We can actually cancel masses out again in this particular situation. So let me rewrite this, get a little cramped there. So I've got g sine theta, sine of 30, minus mu g cosine of 30 equals my acceleration. So from this point we can just plug in some numbers. I've got 9.8, sine of 30 is 0.5 minus mu times 9.8 cosine, I don't remember cosine of 30 off my head, equals the acceleration that we found here from our kinematic information, 0.52083. From this point it's just algebraic manipulation. I don't really have room on this page and don't want to copy it onto the next. So I'll just tell you, when you rearrange all of that, you end up with a coefficient of friction of 0.516. And the coefficient of friction is unitless. So there you go. That kind of puts it all together. Have a good one. See you next time.